Hello, this is Isaac. I'm here to talk about keyword search. This is an important part of pretty much every search system, and understanding how it works will let you build a better search system. There's lots of tools in the toolkit for retrieval, which can be used for RAG or many other purposes. Keyword search is one that works particularly well with technical terms. Most search systems work best with a combination of keyword search and semantic search, and even agentic search. Keyword search is still relevant and is a very foundational tool that's used in quite a lot of use cases. It's very fast, so let's jump into it. We're going to cover how this particular technique works. We're going to go over the key components of it, and we're going to understand kind of each building block along the way. Before I jump into it, actually, this is a brand new site that I'm releasing, kentrolearn.com. I'm going to be publishing lots of educational content. This is a video that's going to go with the Understanding Keyword Search article. In this article, you can go through. It's very detailed. It covers all the code along the way. So if you want more detail, please check that out. This article is totally free. So what is keyword search? First, we're going to find documents by matching on exact words. So if we search for machine learning, we'll find documents with those terms exactly. It's different from semantic search in the sense that it's doing a literal search and not just not doing it based on meaning. So meaning a lot of times things like car versus automobile aren't going to match. That's good in some situations, not good in others. We'll talk about those as we go. When I do say exact search, it doesn't actually mean exact search. We do want things like run and runs and running all to match to run. So there's some pre-processing to make words match. There's very simple stuff, and there's stemming, there's lemmatization. We'll talk about those a little bit later as well. This is very precise, but it is less flexible than semantic search, meaning it's good for different things. Why keyword search still matters. We may have terms for like COVID-19. We need that to match an exact condition, not general respiratory viruses. Or habeas corpus. This is a specific legal term. We want documents that match those exact terms. KYC requirements. These are exact regulatory acronyms. So in many cases, not just the general meaning of the word matters, but actually a term. And it really depends on the domain and the use case and what you're searching for and why. So technical domains need exact terminology. Acronyms, legal terms, meta conditions, this precision matters. And most search systems combine keyword and semantic search, and they combine them. So this is not just a keyword versus semantic versus agentic. In a lot of cases, they combine this and more types of algorithms to give the best result. Today, we're just talking about keyword search. We'll cover the other ones in future articles. So the first thing we need to do is we need to do some text processing. We need to clean and normalize. I mentioned things like we want run and runs and running to all match the same thing. We don't want capitalization. If run happens to be the first word of a sentence versus in the middle of the sentence, we don't want that to match on different terms, things like that. We move into tokenization, which breaks it into these keywords, and we'll talk a little bit about what a word really means. We then do indexing. We need a fast lookup structure, so we will build an inverted index. We'll talk about that. We need to match to those relevant documents, and then ultimately we need to order them. We need to know which are the most relevant one. In the article, we build it completely from scratch and walk through all these, and understanding these fundamentals, even if you don't build them from scratch, will help you build a better search system and have better intuition about when this is a good tool versus not a good tool, why your system might be failing, and the things that might help you fix it. So the first step, text processing. Generally, a simple example of the problem is all of these, if you just split it on the space, will match different words. Kubernetes versus Kubernetes, capital versus lowercase. If it ends with a sentence, a punctuation gets in it. So a very simple way of processing is to lowercase all the punctuation, all the text, remove the punctuation, and then finally stem words. So things like running matches to run. The stemming is actually quite a deep topic. There's stemming and there's lemmatization. And the reason it's deep is it seems like you can just simply say, well, let's chop the ing off the end, and that'll give us a stemmed word. Until you find a word like string, which, ing is part of the word. Stir and string are different, and they mean different things. And it seems like maybe we can just chop the s off of a word to get to plural to singular until you get to a word like yes, where s doesn't imply plural, it implies it's part of the word. And so there's no simple set of rules that removes and takes every word down to the base reliably. Languages don't work that way. At least, real languages that people speak don't. And so typically you use a library like NLTK or something else to do these better algorithms. But understanding what these are doing helps you identify what some of the failure cases are, because they do come up. Stemming is aggressive, but it's fast. You can change implementing to implement, all that kind of stuff. And again, those libraries are the best way to do it. You almost certainly don't want to implement your own. N-grams is another thing. When we talk about keyword search, we don't actually always mean a word. We can mean phrases. So, for example, COVID-19 is a specific term that we may want to match for, and it might match differently than COVID and 19 separately. 19 on its own means something different than 19 with the word COVID in front of it. And so if we look at this, we can do unigrams and bigrams and trigrams. And with unigrams, COVID-19 pandemic response is individual terms. When we group them by bigrams, we get COVID-19, which, these two words in this case should be grouped, and pandemic response. Those two words should be grouped. That gives a little bit better information than pandemic and response. This is the response to the pandemic, not the response to a question or a reporter query or a politician responding to something. And so grouping these together in this sense makes sense. As you build it, COVID-19 pandemic also has a meaning together. Pandemic applied to COVID-19 has a specific meaning that's a little bit different than just a general pandemic. And so by doing these different ways of grouping them and what determines a keyword, you can match on things a little bit differently. So some information exists in phrases, not individual words. Lots of technical domains have many multi-word terms, but it's a trade-off. You have more of these n-grams, you get, bigger index, better precision. And in reality, like with most things, the answer isn't, should I use unigrams or bigrams? The answer is most systems use a blend of both. And so you have a little bit of a hybrid where you can have both. Now, depending on your use case, you might want a different weighting. And so understanding these is very helpful, and how this might apply to your domain, especially as you're seeing what are the actual failure modes happening, what kinds of matches are not working properly. Looking at these unigrams, bigrams, and trigrams can be really helpful. One key note is there is something called trigram search, which confusingly has very little to do with these trigrams. It's kind of a different topic, so we're not going to talk about that today. But just keep in mind these terms do get a little meshed. So this is what I'm talking about when I talk about bigrams and trigrams in this case. Okay, so we've got an idea. We have these keywords. We want to find them. Kind of the dumb way to do it is to say, well, let me just look through every doc every time. Someone searched for a term, a sentence that includes Kubernetes. Let's say, is Kubernetes in doc 1? We check the entire document, see if Kubernetes is in there. Maybe it is, maybe it isn't. we do the second time, the third time, the fourth time. If we've got 5 or 6 documents, that's fine. No problem. We can do that. If you've got 10,000 documents and every time anyone searches, you're going to search 10,000 times for each term, it's going to be too slow. Or if you have 100,000 documents or any kind of set. And really, that's something we can calculate ahead of time to make it much faster. And so we build what's called an inverted index. We need a better data structure. And what the inverted index does is it does all that check ahead of time so that we can do that check very quickly. So, for example, this inverted index says Kubernetes, that term Kubernetes, is in documents 1, 3, 7, and 15. We know what all the terms are in our data set, and we know we're going to be matching our terms to documents. And so building this index lets us say anytime we need to look up Kubernetes, we can do a simple lookup, find Kubernetes, and we have all the documents. We don't need to search every single document. It's an instant lookup. The key idea here, and this is in semantic search and other places as well, but that for search, often we are searching against a knowledge base that we have. Maybe that's Wikipedia, maybe that's internal company documents, maybe it's movie scripts. We're searching for something, and a lot of these documents are going to be relevant. And so we can pre-compute some of the things that we know we need for search to make it faster for the user. So we trade a little bit of storage for speed. In this case, this index is a very good trade-off because you get much, 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 much faster, and it doesn't take much space. Interestingly, when you have this, now these kind of Boolean operations and filters, if you're on like Netflix or something, or you're on any kind of search site where you can have and or filters, those become very easy because you don't need to search through all of the documents. You have an index for Python and an index for machine. We can see which documents contain Python. We can see which documents contain machine. And we can just do set operations. We can do an and. Cool, 2 and 2, that's in there. We can do which ones have either. Okay, 1, 2, 3, 4, and 7. It's done. I don't have to look anymore through every single document and all the text to do these operations and build out a traditional, manual filter and give users some control there. And it just gives, really precise control. Not all matches are equal, however. We need ranking. We probably don't want every single document that just contains Python and machine. We probably want to rank those for the ones that are most likely to be relevant to the query. All right, so the ranking problem. We may have 2 documents that match Kubernetes. If we have document A mentions it 20 times, that could be a very focused tutorial. There might be another a document that is talking about deployment and containerization generally, and is talking about, Kubernetes in passing. Maybe it's about Docker, and it just says like, hey, and if you want to scale Docker up, use Kubernetes, and that's all the mentions it once in passing. It's clear that in most cases, you probably want the tutorial that's talking about Kubernetes quite a bit. And so we can use this term frequency to rank one higher. Boolean search matches all equally. It would say, hey, look, Kubernetes is in both of these documents, so return both. We want to measure relevance. This is where these algorithms, TF-IDF and then BM25 that builds on top of that come in. We say, this one is more relevant than that one, so we're going to return it first. TF-IDF does this exactly. So term frequency is just what it sounds like. A document with the term Kubernetes 10 times is going to be better than the document that only mentions it once. IDF is inverse document frequency. And so it wants to rate terms that are more rare higher. So for example, if I have a data set talking about Python, and every single document in my data set contains the word Python somewhere, because it's just a data set of Python programming terms. And so every document contains the word Python. That is not a useful search term. And so it's going to give very, very low weight. However, maybe PyTorch, the word PyTorch only appears in 5% of the articles, and Kubernetes only appears in 1% of the articles. Now, if someone searches for Kubernetes, we can really narrow it down, or PyTorch, we can really narrow down the query quite a bit with just that one term, meaning that term helps us find relevant content more than the term Python, because every article is about Python. That doesn't help us determine which one we need. Whereas these rarer terms that are only in some documents help a lot more. And that's the idea of the inverse document frequency. And we're going to pair these up. We're going to say, hey, look, if you have a term, the more it shows up, the more valuable it is. However, terms that every document has, we don't care as much about, as opposed to kind of rare terms that make this particular document, very unique. So a word like the would get a super low IDF score. It doesn't really matter how many times the appears in it. It wouldn't really have much. It works well, but it does have some limitations, which we're going to talk about here in a minute. So BM25 improves on it in many ways. We want diminishing returns. So for example, we talked about term frequency. One way to do it is to say, hey, if it mentions the term Kubernetes once, it gets a score of 1. If it mentions it 10 times, it gets a score of 10. This is problematic for a few reasons. One is just because a term is mentioned and you stuff it a lot of times, that doesn't mean it's more relevant. There is a signal there. You want things that are really about the core topic often and not just are mentioned in passing. However, you also don't want to return something that just stuffs a bunch of keywords in there. And so you don't want to weight too heavily on just one term. You want a little bit of a balance. If a single term of a 10-word query is in the article 100 times, but none of the others are, I don't want that to overweigh everything. So this is this diminishing returns. If it's mentioned once, it gets a gold star. If it mentions twice, it gets 1.4. It doesn't linearly scale. Every successive mention does help of this one particular term, but not to the point where, it linearly scales. And so there's diminishing returns on how many times you can add a keyword in there. And this helps with keyword stuffing and things like that. The second thing it does is length normalization. So if all we're doing is saying how many times do these keywords show up, well, a longer article is always going to have an advantage over a shorter one. An article about Kubernetes, which is 4 paragraphs long versus one that's 8 paragraphs long. On average, the one that's 8 paragraphs long might have twice as many words, but be just as relevant. And so we want to have some sort of length normalization and not just say, hey, look, we're always going to try and return longer articles because they have more relevant keywords. We're going to say, let's normalize based on length and say how relevant is this topic, not just how many total keywords are in there. And so this length normalization adjusts for this idea that long documents obviously have more words and adjusts those scores. And the third is, it does better inverse document frequency, and it does some smoothing just to make it a little bit more stable and handle some edge cases. So this BM25 is what is most commonly used today. So generally, the idea is, user types machine learning. This text might get processed to machine and learn. unless you're using a bigram, in which case you'd want to keep machine learning because that's a specific term. It looks up in this index, and we get a score. And then now we say, cool, this has the highest score. This is best. Let's return these documents in order. The reality is you need to. If you return 50 results and the first 10 aren't relevant, your user's probably not going to look at number 11 or 12 or 13. And you're probably not going to stuff context with 50 documents. So you want the top most relevant ones at the top, both if you're returning it for a user or if you're doing like RAG. And this works extremely quickly. So, all these work together. This optimization matters. And it's a foundation for more advanced search features. Often this is a pre-filtering step, then you do a next step called re-ranking. Often it's combined and weighted with semantic search. And it tends to have more weight the more, specific and technical the domain is. So key takeaways here, this keyword search, it's not magic. It's just kind of some clever engineering. There's no topics that are, or ideas that are super mind-blowing. If you understand them, they're relatively simple. They're just combined together in a really powerful way. The text processing makes this matching reliable, whether that's how you strip them and how you stem them and all this. And understanding that is important because you may find that there are terms that doesn't work well with or that aren't going right, particularly if you have some terminology that's not super common or common at all. Inverted indexes are what makes it fast. This is your basically pre-calculation of stuff. You're going to calculate a bunch ahead of time, so it's fast at inference time. BM25 is doing some ranking to make things pretty relevant. It's accounting for length normalization. It's doing some smoothing, and it's doing diminishing returns on your keywords. And again, the key here is that this is a tool mostly when you have really exact terminology that you need. It's not the right tool in every case, but in many cases it is. A lot of these principles apply everywhere. When we talk about semantic search, we'll see we do pre-calculation to make it work. We calculate the embeddings advance. We do a lot of the same tricks. Cool. So if you want to learn more, this is a free article. I'm working on a RAG course for backend developers currently. I'll probably do some other courses as well. It covers keyword search, semantic search, hybrid search, re-ranking, agentic search, LLMs for like summarizing results, and there's a lot of stuff that's being worked on. It's going to be on boot.dev. Check out the article, and there's a link in there for a discount code if you're interested. Check out the article, and on the website there's also a link to the Discord where people can join and learn about stuff on this site, but just stuff in general, other content as well. All right, thanks for joining.